So welcome to STAMPS. Today's speaker is Dr. Elizabeth Barnes. Dr. Barnes is an associate professor of atmospheric science at Colorado State University. She received her PhD in atmospheric science from the University of Washington. Dr. Barnes' research is largely focused on climate variability and change, and the data analysis tools to use to understand it. So topics of interest include Earth system predictability, subseasonal to decadal prediction, explainable AI, and data science methods for Earth system research. Dr. Barnes is involved in a number of high-profile research activities. She's the lead of the US Climate Working Group, Emerging Data Science Tools for Climate Variability and Predictability, a member of the National Academy's Committee on Earth Science and Applications from Space, and senior personnel at the NSF AI Institute, AI2ES, for trustworthy AI in environmental sciences. So the topic of today's talk is benefits of saying, I don't know, when analyzing and modeling the climate system with machine learning. Libby?
Thank you very much. And you can hear me? Yes? Perfect, thank you. And thank you for the invitation. So you've already heard a lot about me, but just a little bit of background. I am very much a climate scientist, and I know this is a broad range of disciplines here on this webinar. So my hope today is not to teach everything to everybody in this talk, but to maybe teach you a little bit about how, as a climate scientist, I'm thinking about applying machine learning and uncertainty to thinking about the climate system and how it may evolve, both in terms of weather to weather timescales out to decadal timescales under climate change, etc. So that's the goal for today. All right, let's get started. So what makes my job so interesting? The concept of chaos is really where to me it makes me so excited, because it means, man, this is a hard problem. So the concept that, many of us have heard, the flap of a butterfly's wings in Brazil sets off a tornado in Texas, or put another way, that small differences in those initial conditions can lead to enormous differences in the final phenomena. I love this line here: prediction becomes impossible, which doesn't bode well, obviously, for someone in my field of research. So the question is, can we show that prediction is not always impossible? That's the question. So the idea here is, that the Earth system is exceedingly complex and often chaotic in nature. So making predictions is incredibly challenging. We cannot expect to make perfect predictions all of the time. And this leads us to this concept that we call forecasts of opportunity. Here we go. So the idea that certain conditions lead to more predictable behavior than others. Now, beyond the weather timescales, as I said, that first slide about chaos, we have this feeling that beyond the weather timescales, prediction may become impossible. What can we do about that? And the idea is that beyond the weather timescale, in climate science, we have to look for specific states of the Earth system, or these opportunities that lead to enhanced predictable behavior. Now, many of you may be familiar already with the concept of this, or the idea of the, as an example, the El Nino Southern Oscillation, or ENSO, which is this climate mode of variability where during an El Nino, we have these warm sea surface temperatures in the tropical Eastern Pacific, and during La Nina, cooler temperatures. Now, these ocean temperatures fluctuate up and down on time scales of multiple years, and we know that these fluctuations can lead to changes in precipitation, so how wet or dry a region is across the globe. And the important point here is all of this knowledge we're getting about, say, rainfall patterns during El Nino or La Nina is only really applicable in this scenario when there is an active ENSO event. So the idea here is that finding these forecasts of opportunity is sort of one part of our trick here. So it's part of the goal of what we need to do to be able to get beyond this prediction limit of, prediction becomes impossible. So a few questions we want to ask are, one, when? Under what conditions do we have these skillful forecasts of opportunity? Why? So this is the sort of the science part, where is it coming from? Why is it there? What are the mechanisms driving this? And finally, once we've answered 1 and 2, how might we leverage these opportunities in a prediction setting? Now, I already gave an example of ENSO, but another example that leads to these global impacts from modes of climate variability is something called the MaddenJulian Oscillation, which is a climate phenomena that can influence weather across the globe via its teleconnections. Now, specifically, this particular behavior has to do with wet regions and dry regions in the tropics that move slowly to the east over a matter of days to weeks. Now, this movement of these storms can then excite waves that travel throughout the globe and can change the direction of the storm tracks, which send, say, precipitation up to Alaska, or have it instead hit the west coast. So if you will, sort of like it can modulate that conveyor belt that's sending moisture and wind to different places. Now, we know that these climate teleconnections, when active, can potentially lead to information, again, information that we can use to make predictions. So as a very specific example of how we might be using this, we have been using neural networks in my group, and I'll go into more detail in a little bit, neural networks to try to understand these teleconnections and how they are modeled in current state-of-the-art NOAA weather prediction systems. So here's Jack Cahill, a master's student in my group, who's taking pictures or inputs of convection in the tropics. In this case, it's called outgoing long-wave radiation, inputting one of these pictures for, say, today into a neural network, and then outputting whether the current NOAA unified forecast system will have a large negative error in that precipitation somewhere else on the globe, a large positive error, or whether that prediction by the NOAA model will be actually pretty good. And here's what's interesting, is you can look at the general accuracy of this model. How good is it at predicting if the NOAA's model is going to have a good prediction out 10 to 14 days? So this is about 2-week timescale. But if you actually then subdivide those predictions by how confident the network is, which can be assessed in various ways, in this case, we're just using the output probabilities by the model, you actually see that there are certain samples that the network was far more confident in its prediction than others. That is, the neural network has identified only certain time periods and samples when it thinks, hey, I know that you're going to have a good forecast, or I know you're going to have a bad forecast. Now, on the same idea, Kirsten Mayer in my group, a PhD student, has done something very similar, but now not looking at forecast errors, but actually trying to make the predictions themselves. So she's taking, in this case, data, this is observational data, inputting maps again from the tropics because of these known modes of variability that can impact the through teleconnections, the weather across the globe. She inputs one of these maps again into a neural network and wants it to predict what the circulation or the winds will do over the North Atlantic 22 days later. So now we're on the order of 3 weeks into the future. Again, we think the tropics is linked to the North Atlantic via these teleconnections. So we have a reason to believe that there might be some information here. Once again, if you look at the total accuracy of her network, which if you can see my pointer is this green line right here, it's about 56% or so, which random chance, by the way, is 50% in this problem, the way we've set it up. So it doesn't look terribly exciting. That's practically a tiny, that's a tiny bit better than random chance. But if you instead then go and focus on the network's most confident predictions, you see that you can do a much better job for certain opportunities or certain conditions when the network does a much better job of predicting the North Atlantic circulation based on the tropics. And again, we think this has to do with these forecasts of opportunity. Now, as scientists, we're not going to stop there. Our question, of course, is why? Why are there some samples or some conditions in this case that are more predictable than others? And this is where my group has really been doing quite a bit of work lately for climate, which is in the area of explainable AI. So I'm going to take a pause here and tell you a little bit about that. And then we'll come back to this problem of asking why are some of these states more predictable than others? So opening the black box with explainable AI, this is a big topic in all fields of machine learning. In climate science or atmospheric science, there have been multiple papers that have come out in the last few years demonstrating how XAI can be used for the geosciences specifically. And one of the tools that my group has been using quite a bit is called Layerwise Relevance Propagation, This LRP is just a little bit less of a mouthful here. This was developed by the computer science community, and it works something like this. And there are many, but I should mention there are many methods like this out there. This is just one that we have found useful. So the idea is LRP works like this. If you have a neural network and you have, let's say you want to predict the probability of a cat being in your image, and you've trained your network already, you push an image through the network and it outputs a probability of a cat is, say, I'm just making this number up, 0.8. You say, okay, that's nice, but where did this 0.8 come from? Why 0.8? Where in this image did the network look to come up with this value? So what LRP does is it takes this 0.8 and it propagates it back through the network to create a heat map of the most relevant regions for the network's prediction. Now, in this case, it highlights that the cat, the region of the image with the cat, is the reason the network came to the conclusion that it did, which is perhaps not surprising. It looks at a cat to know there's a cat in the image. But let's take this a few steps further for why explainable AI might actually be incredibly useful for these applications, these climate applications I'm talking about. So if you've seen my talks, you've seen these slides because I give these in all of my talks. I think these slides are really fun. So I will step you through it if you haven't seen this one before. So here's an example of why you might want to use explainable AI. So, and again, this is not work. This is actually work done by Lapushkin et al. From 2019, but I love showing it off. So here we go. We have some images of horses, and a network was trained to identify the probability of there being a horse in each image. And the network does a great job. It says there's horses in each of these images, and hopefully you can see on your screen there are indeed horses in each of these images. So then the authors used Layerwise relevance propagation to create heat maps of where the network looked to determine there was a horse. And if you ignore the blue for now, you look at the red, you see that the most relevant regions for knowing there was a horse was where there is a horse, something like the cat example. And you say, okay, nice. Maybe my network is doing something reasonable here. But then they go on to show another set of examples. And here are 3 more horse images. Hopefully you can agree there are horses in each of these as well. And the network also predicts there are horses in each of these images. But we can then apply Layerwise relevance propagation to once again make these heat maps. And what we see is that the network is not putting most of its relevance where there's a horse, but instead focusing on that bottom left-hand corner of each image. And if you go back up to the top and you look, what's in the bottom left-hand corner is not a horse, but instead it's a copyright symbol. That is, the network has learned that this copyright symbol means there's probably a horse in the image, and that's because this training data was actually scraped off the web, and most of the horse images came from this one German website. So this is an example, I think, of where explainable AI can really help us ensure or learn whether our network is getting the right answers for the right reasons, which again, in climate science is, and I would argue in most science, is incredibly important. So why would we want to use XAI for our geoscience applications of machine learning? A few reasons. One is like I showed you, to identify problematic strategies and the learning strategy of the network. 2, to evaluate trust. Again, if you know it's not doing something for the wrong reasons, you might start to trust that these predictions are actually worthwhile. 3, to choose the actual approach in the first place. We've actually used it to decide which particular inputs are being used most often by the network, so we can change our architecture and how we input our data. And 3, and this is the one that we're having the most fun with, I think, is learning something new. That is, if we set up our machine learning problem to take in some input and create a prediction, we may not actually even care that much about the prediction, but instead we might use explainable AI methods to look back at the input and ask, what did the network learn in the data? How was it able to make the prediction that it did? And that may be where the science is, not in the prediction itself. So let's go back to this example a few slides ago. So here, what we're doing is inputting tropical information and then having the network predict what the winds are going to do over the Atlantic 22 days later. Once the network is trained to do this prediction task, which it was, we then can use explainable AI methods to propagate those predictions back through the network and create heat maps of the relevant regions in the tropics for knowing what's going to happen in the Atlantic days later. So we've done this, and we can end up with maps that look something like this, where the colors here denote, so the shading, the blue, denotes the regions that are most relevant for the network's prediction. And what it turns out we see is in the top plot that this is a sort of a canonical MaddenJulian oscillation pattern, as we thought it might be. But that in the bottom panel, we actually see a new region of interest that we weren't aware should be something we should be looking at for this prediction problem. And thus, we can now go out and set up dynamical model simulations and start to try and understand why was this region picked up by the network and what is so important for teleconnections to the North Atlantic. So for all of this so far, this has actually been set up as classification problems, trying to set up our network to predict one of a few classes. And in that case, we can talk about the certainty of our network, or how certain our network is. If you recall, we like to take the most certain predictions and analyze those. But for classification, that's pretty straightforward, because the way it typically is set up is the network outputs some sort of likelihood, and we can use that to filter out the more likely or less likely classes. However, for regression, which is what a lot of climate scientists like to use, this is not so obvious how to do this. Typically, when we set up a neural network regression problem, we're taking an input, putting it through a network, and outputting one single value without any certainty or uncertainty quantification from that network. So what we've been doing, there are many, by the way, I am aware there are many different ways to add uncertainty in machine learning, and it's a vibrant area of research. I'm going to tell you how we're using one of the simplest approaches we have been able to find to explore some of these concepts of forecast of opportunity. And the idea is, it's very simple. And again, it's not new. What we're going to do is we're going to have our input, but instead of training a neural network to predict a single value, we're going to train a neural network to predict a conditional distribution of the value y based on that input. Now, in the few cases in my field where people are already starting to apply this, they assume a Gaussian. That is, they predict the mean and the standard deviation of that y, so that conditional distribution based on their input. And here what we have found is that's nice, but if you don't expect the conditional distribution to be symmetric or Gaussian, that can have some problems. And so we have been using this function here called the hyperbolic sine arc sine family of normal distributions, which takes in 4 parameters. The reason I really like it is it's pretty intuitive for someone like me, because if the last 2 parameters are set to 0 and 1 respectively, you get the straight up Gaussian. However, by varying the 3rd and the 4th parameter, you're able to get skewness in either direction, allowing the network to learn uncertainty and this conditional distribution when it's not Gaussian as well. So let me just show you sort of the idea here. How does this work? Imagine this is your data. It's very simple. This is just an X and then the Y here. So you have some data here, X. If you look at it, the spread of Y is certainly a function of X. So if X is 0.3, Y is well constrained, whereas X is 0.5, there's a much wider conditional distribution of Y. We want to train our neural network to not only predict Y, but also predict this distribution of orange dots. So when we train the neural network in this way, and I'll tell you how we do that in just a second, we get something that looks like this, where the blue lines denote the 80th percentile bounds of the predicted conditional distribution, and the orange shading is the actual 80% percentile envelope, showing that the network, when necessary, is learning that in some cases and for some X's, there is less certainty than others. Now, I'm aware this is a very simple example, just to get the idea across. Now, how is this training done? How do we learn to predict these 4 parameters of the conditional distribution? This is just based off of maximum likelihood estimation. Namely, what we do is our loss function in training this neural network is just minus log p, where p is the predicted conditional distribution evaluated at the true value y. And so in this way, if you're unfamiliar with this, this is how these are the pictures I made, my Goldilocks plots to think through this. If your network is overconfident and predicts too narrow of a distribution, when you evaluate y within this probability density function, you're going to get a small value, and thus you're going to get dinged a lot in your loss function. Similarly, if your model is underconfident, that predicted distribution is very wide, and again, P is very small. And so the network is trying to find the right set of parameters for each prediction such that that P is maximized. So just to show some nice visual examples of how we're using this before I jump back into this concept of forecast of opportunity, we've recently started applying this to operational hurricane forecasts. And by operational, I mean where we're working towards it. They're not operational yet by any means. But the idea being that if we have, so the consensus here is the yellow line. This is currently the guidance that the National Hurricane Center is getting for certain intensity forecasts for different hurricanes. In this case, I believe this is at the 48-hour lead time. So 48 hours in advance. The truth is the blue. And we are training a neural network with this distribution to try to predict the conditional distribution of the truth. So in this case, our neural network shown here in pink predicts on the top for Vicky, predicts a value close, its median is close to the truth, but it also predicts a high or a large tail. Similarly, we're applying this to track forecast to try to get simple uncertainty bounds with a simple neural network on where the hurricane may end up in the next few days. Now, this is us, sort of messing around with this simple way of adding uncertainty, but let's go back to forecast of opportunity. If you remember, the whole concept is we want the network to give us some amount of I don't know, so we can sort those predictions and find the ones where the network's most certain to explore where that opportunity for forecast skill is coming from. So Emily Gordon, a PhD student in my group, is doing this for climate predictions. Specifically, she's looking at ocean heat content and trying to predict future sea surface temperatures 1 to 5 years in advance. So this is a much longer time scale than, say, 48 hours here. And when she does this, so what she does is she takes a map of today's ocean heat content, puts it into a neural network. And in this case, she wants to predict what the sea surface temperatures will be over the Atlantic in 1 to 5 years' time. In her scenario, it turned out that a simple Gaussian worked fine. She didn't need all 4 parameters of that other distribution. But what she finds is the error drops drastically on the predictions when she focuses on the 30% most confident predictions. That is, only the most confident predictions here have this sudden drop off in error. And this suggests that maybe something interesting is going on here in terms of this forecast of opportunity. Now, this is all just sort of analyzing the uncertainty of the network after we've trained it, after we've run our sample through. So where I want to go now is the concept of how can we incorporate this uncertainty while the network is learning. And this is what we call controlled abstention networks. So the big idea is this new loss function called the abstention loss works by incorporating uncertainty into the network's prediction to identify the more confident samples and abstain or say, I don't know, on the less confident samples. That sounds a lot like what I've already been talking about. But the important part here is the abstention loss is applied during training and thus preferentially allows the network to learn from the more confident samples more. That is, not get as confused on the samples that maybe there was nothing to learn because they were relatively unpredictable. Now, we've developed a methodology to do this both for classification and regression tasks. I am not going to bore you with all the details for both. So instead, what I'm going to show you today is just how we've been using this for regression tasks specifically, since that is more of the novel part of this work. The classification task, the idea of an abstention network, was previously developed by a graduate student in 2020 out of University of Washington. And so I highly link you to that paper as well. And that's, again, a computer science application that we are bringing over into the climate field. All right, so how do these abstention networks work? The idea is during training, we want the network to estimate some amount of uncertainty for each prediction, and then implement a loss function that learns to identify the more confident predictions and learn them better. And then we need to compare it to something. So we're going to compare it to a baseline method that only filters out samples post-training, just like I've shown you in the first part of this talk. So that's going to be our baseline approach. Let me show you how that's, or just show you once again how that's done. So the output from the neural network or the model is a distribution for each sample. So we push in a sample through our model and we get some predicted distribution. We do this for many samples. We get many predicted distributions. The more narrow, the more certain, the more wide, the less certain. And the idea for our baseline approach is to filter out the least certain. So that is keep the X% most certain. And that's our baseline, because that's already a pretty good way to assess which predictions are the most certain and to see if they're actually the most accurate as well. So now for the new part. Now it's to apply abstention during neural network training. So there's a lot of details here that I won't go into all of right now, but here's the general concept. Here is we are going to set up our abstention loss that is of the form equation 4. And if you look here, you see a minus log p hiding within it. So it's based on this maximum likelihood estimation idea. However, a few additional terms that show up that allow you to control the amount of abstention. And what I mean by abstention is allowing the network to say, I don't know, I'm going to ignore that sample, or I don't know, I'm going to pay less attention to that sample than other samples. Otherwise, if you don't have this term, the network will just abstain and say, I don't know on everything in order to minimize its loss. And that's not the goal here. There are a few other aspects to these equations I'm not going to go into, but one of them, one quick thing is that the way this works is we have set up the code to run in 2 ways. One is that the abstention fraction can be set by a PID controller. That is the user can go in and choose what abstention fraction it wants, and this controller will force the network, like is shown here in this plot, to abstain on that exact many samples, or exact close to that many samples. Or the user can try and have the network predict the optimal abstention fraction for the best learning. And both of those are options. So before showing you more complicated examples, I'm going to go back to sort of just an XY example because it's easy to visualize. So this is how actually we started the project. As I made this plot and I said, I want a network that can do this. And here's the idea. Imagine I had a situation where 80% of my data fell into this big blob, and only 20% of my data fell onto this very nice thin line. Now, trying to fit a line through all of this data would be a total mess. And so what I want is a network that can identify that those 80% of those samples are relatively unpredictable, and that the 20% that fall along that nice line is what I want it to learn. And so the question is, can we train a network to do this? The answer is yes. With this abstention methodology, we are able to train a neural network to predict. It learns to only predict 20% of the samples. I didn't actually tell it to do that. It learned to only learn 20% of the samples, and it learns them very well, as shown here in the blue dots lying nicely along that one-to-one line. Now you might say, this just sort of seems like a lot of work. Why couldn't we just done that baseline approach where we trained a neural network the more standard way, and then at the end of training, after it was all done, we assessed the most certain predictions and just looked at their accuracy? And so we need to compare our baseline approach with this CAN, or this abstention network. So I'll explain this plot here. What I'm showing is the mean absolute error of the predictions on the y-axis and the coverage percentage, or how many samples the network did not abstain on. So it's the percent of samples the network did make a prediction for. The thin purple line is our baseline approach. So that's what we would get if we filtered the samples after the fact. And the orange dot here is what we get with the CAN. That is, the abstention network slightly, I realize it's not a big difference, but slightly outperforms the more standard approach, and the abstention network itself figured out that it wanted to abstain on approximately 80% of the samples and only make predictions for the other 20. So this is very, very simple, and I am certain there are other ways to do this problem that do not require neural networks or abstention networks. But this is merely to show the concept here. So let's go to a more complex example that's far closer to something we might see in climate science. So this is using synthetic climate data created by my postdoc, shared with Ebert Upas, Dr. Antonius Mamalakis. And he created this synthetic data set to try and mimic many of the properties of observed sea surface temperatures, so climate fields, while still allowing us the synthetic aspect to be able to play around with it to use it as for testing for some of our methods. So the idea here is that he has different samples. Each sample is a map with spatial correlations similar to observed SSTs. And from this map, he pushes each map through a known nonlinear function of those SSTs to create a single value y for each sample. Now, the function f is actually not important here. I can talk about it later if you're curious, but the point is there's a nonlinear function that connects a map of synthetic sea surface temperatures to a single value. So if we wanted to set up a simple neural network, which he does in his paper, one could input this SST map and then see if the network could learn this nonlinear function to predict y, this y that we've given every map. Now for my application, actually, that's not what I want to do. What I want to do is I actually want the network to predict, in this case, the mu and the sigma of that conditional normal distribution. So give me some amount of uncertainty with each of its predictions. Furthermore, I want to try and link this back to the concept of forecast of opportunity. So I'm going to go into this synthetic data and I'm going to mess with it a little bit before I do any training. And here's what I'm going to do. I'm going to go into this data, which currently has a perfect mapping from the input to the output. And I'm going to go in, and whenever there is an ENSO-like signal or an El Nino-like signal in the sea surface temperature map, that is, whenever the tropical Eastern Pacific, the values there are greater than 0.5, I'm going to leave that sample untouched. But then all other samples, I'm going to shuffle the Y values from that input. In the end, I'm going to have 71% of my samples shuffled, what I call corrupted. That is, the input and the output have nothing to do with each other, or they are incorrectly labeled. And only 29% specifically El Nino-like events are the ones when I have not touched and have a link between that input and that output. So the idea here is that only samples with strong El Ninos have a learnable relationship with their labels. This, if you will, is my forecast of opportunity, or my opportunity to create an actual skillful forecast. With this data set, we go through once again, and we can train our baseline approach. We can train an abstention network, and here are the results we get. In this case, again, mean absolute error is on the y-axis, so you're better if you're lower. The purple shading is what you get with this post hoc analysis. So when you're looking at your uncertainties after the fact, that is filtering by sigma from that predicted Gaussian. And then the dots are what we get from the abstention network, which is allowed to learn the more certain samples better during training. The big point here that we see is that the abstention network outperforms the baseline approach in every case at these coverages. And this, it turns out, if you recall, about 29% of my samples were learnable, actually had predictable behavior. And the abstention network has figured that out and improves over the baseline approach. Now, we think the abstention network can be used for more than just this one example. We have found for other use cases, it can outperform if you have corrupted inputs, so it can act as a data cleaner, so it doesn't get confused by noise or corruption in your data. It can help you identify forecasts of opportunity, as I just showed you. And two other examples I haven't shown you here, but are in the paper, is if you shuffle certain sample labels, or if you just have arbitrary label noise. It is able to identify these and not learn from, if you will, not get as confused from those noisy samples as the more standard baseline approach. Okay, so wrapping up here, and I guess I want to end here with a few sort of big ideas, because I know some of this seems very specific. So the idea of forecast of opportunity, sometimes I don't like the fact that I have the word forecast here, because a lot of people think this means it only applies to weather or climate prediction. And that's not the case. Perhaps a better phrase is state-dependent predictability. But either way, I think in many, many geoscience applications, not all samples are expected or situations are expected to be as predictable as others. And sometimes I wonder if when we're using these sort of brute force machine learning methods, if we're not wasting some of that energy having those networks try and learn relationships that we already know aren't predictable. And so I think this is something we really want to think about as we move forward for our specific applications. So let me leave you with some of my final thoughts here. The first is what I'm talking about here is more than just uncertainty quantification, and it's more than just a post-processing application. I really think it is worthwhile for anyone working on AI for climate science to consider taking this mindset of forecasts of opportunity when approaching climate data. Next, I brought this up, but I think it's impossible predictions may be hampering the learning of predictable behavior. So, for example, again, predicting climate variables or dynamical forecast errors. And I'm wondering if this could be helpful to filter out those harder predictions, either to ignore them or to train them separately because they're harder and maybe require a different architecture or approach. Number three, this is very specific to climate models, but there's a lot of work right now being done and thought about for machine learning for climate model parameterizations, where we're trying to simulate subgrid scale processes, and we need some parameterizations to allow us to do this. And one question is, could we use approaches like this, again, simple uncertainty quantification or this abstention approach, to actually do it in line while the climate model is running, to kick predictions to the machine learning parameterization or to the physics-based parameterization, which is slower, but potentially more accurate in real time. Furthermore, potentially with these uncertainties, could this be helpful for out-of-sample climate change samples where maybe the network has learned that it should abstain when a certain sample is outside of what it was trained on? And finally, I think the utility of this whole concept generally revolves around the fact that we have a small, in quotes, amount of data to train on. I think if we had lots and lots of data, presumably the machine learning algorithm could figure out what to ignore and what to use. But very rarely do we have enough data, I think, for this to actually happen, which is why I think that thinking through this idea of forecasts of opportunity for when applying machine learning can have some benefits. So with that, I will just push this up since there's a recording and then go back. So you can pause it if you want to see references. Okay, thank you.